Water where it shouldn't be. A rocky world, 36-hour year. Dayside near 865 Fahrenheit. Webb sees water vapor, but red dwarf star spots are cool. They mimic atmospheres. 2 models, 1 spectrum. Atmosphere game changer. Star spots mirage. Which one lies, the planet or the star? Will cut through heat and light. No water equals life. Are you ready to test the impossible water? "26 light-years away. The system GJ486, an M-class red dwarf, cooler than the Sun, smaller, flare-active, a simple spectral background but temperamental from spots and flares. Orbiting the star, GJ486b, a dense, rocky super-Earth. Radius about 1.3 Earth radii. Mass roughly 3 times Earth's mass. Gravity is strong, holding a searing surface. The orbit is ultra-tight. The year is about 36 hours, 1.5 Earth days per loop. Star-planet distance, only a few million kilometers. Irradiation is extreme. There are no breaks. The dayside temperature, around 800 degrees Fahrenheit. That is about 425 degrees Celsius. Hot rock. Local melts in darker regions. Trace metals in vapor. Water is unstable under these conditions. Any atmosphere suffers continuous loss from heat and particles. The world is almost certainly tidally locked. One hemisphere in endless day, the other in endless night. Between them, a narrow terminator with sharp gradients. Supersonic winds are possible, but not guaranteed. Heat transport can be weak without a thick envelope. Red dwarfs are flare-prone. Ultraviolet and proton events break molecules apart. Coronal mass ejections accelerate the loss of light gases. Magnetic activity varies by cycle and can surge suddenly. For close-in rocky worlds, this is the harshest regime. The James Webb Space Telescope detects a transit signal. During passage, part of the starlight skims the planet's limb. Molecular lines carve measurable dips in the spectrum. Water leaves a characteristic rise in the near-infrared. On GJ486b, that signature is present. A contradiction emerges. A rocky planet, hotter than a kiln, under constant bombardment. Yet the data show a water signature. If this is planetary air, the story shifts. If it is not, the source must be different. GJ486 is a nearby laboratory for rocky worlds. The star is small, so transits are deep. Even a thin column of molecules can be detected. But stellar structure adds noise and mimicry. Unmodeled star spots can inject similar lines. Net scale, a compact system. A red dwarf, a hot rocky on a very short orbit, likely tidally locked, with a dayside near 800 Fahrenheit and an active star. Transit data show a water signature in the infrared. The source still needs to be separated cleanly from the star's background, and that separation will decide what we call atmosphere here. This is about transit spectroscopy. When a planet crosses the star, part of the light skims the limb. If gases are present, molecules carve depressions in the spectrum. Water leaves a characteristic near-infrared pattern on GJ486b. That pattern is detected. This is about repeatability. Multiple transits show a similar shape. Amplitude holds within uncertainties. The bump peaks at short, near-infrared wavelength. That aligns with water vapor lines. This is a rocky planet around a red dwarf, 26 light-years away. Orbital period, about 36 hours. Dayside, about 800 degrees Fahrenheit. Such a world is not expected to retain a thick atmosphere. That makes a persistent water signature notable. Two explanations compete. First, a diluted planetary atmosphere with traces of water vapor. Local, thin, possibly transient vapor. A small column still leaves a spectral signature. Even short-lived vapor can imprint transit absorption. Second, star spots on the red dwarf. Cooler photospheric regions with richer molecular lines. Water survives there, the spectrum darkens on water vapor features. If the spot coverage is significant, the contribution can mimic air. The observable effect, the same water bump in transit data. This is about modeling, not a single picture. The full wavelength-dependent light curve is fitted. Two physical schemes are compared, atmosphere versus star spots. Both reproduce the observations plausibly. Statistically, neither is ruled out. This is about systematics. Activity variations are accounted for. Independent reductions are cross-checked. Alternative molecules and aerosols are tested. Carbon dioxide and carbon monoxide fit the shape worse than water vapor. This is about method limits. Transit spectroscopy probes the planet's edge. Sensitivity sits near microbar levels. Everything in the light path contributes, planet and star together. With strong spot coverage, signals mix. Without external anchors, background can pass for atmosphere. This is about what is already excluded. A thick hydrogen-rich envelope would broaden the signal. Opaque clouds that mask lines do not improve the fit. Planetary dust does not reproduce the water vapor peak. Two realistic paths remain: thin vapor at the planet or water in spots. Assumptions matter. In the atmosphere scenario, a short-lived high-altitude vapor layer is allowed. Sources include degassing, mineral evaporation, or night-side transport. The column is small yet detectable in transmission. Heat transport can stay weak. Daytime emission need not look wet. A hot rock can glow like bare stone and still carry a thin limb signature. In the spot scenario, the physics is starker. Cool regions on the star host stable molecular lines. During transit, the planet masks part of a spot. The system spectrum shifts. The transit curve acquires a water imprint without planetary gas. How to tell the stories apart? Use wavelengths where the models diverge the most. Use measurements beyond transit only. Use secondary eclipses for dayside brightness temperature. Use added bands to control spot contamination. Status. Today. The transit water signature is real, robust, reproducible. Its origin is not clear from transmission alone. Two models remain on the table. What is at stake scientifically? If it is a rocky atmosphere, the air detection threshold moves. If it is star spots, candidate selection and vetting change. Either way, joint observations rise in value. Planet and star must be treated as one coupled system. Otherwise, a water signature is easy to misread. What comes next? Days and nights of GJ486b are probed via secondary eclipses. Dayside brightness temperature is being refined. A thick atmosphere scenario is losing support. The transit water signal remains. Honest uncertainty remains part of the story. The signal is visible. The mechanism is debated. Additional bands and observing modes are critical. Those tests must separate vapor at the planet from water in spots. That is the core of the finding and the next step toward a verdict. August 2024, secondary eclipses of GJ486b are published. A different method, measure the drop in total light when the planet slips behind the star. From that drop, extract dayside thermal emission and brightness temperature. The dayside is hot, around 865 degrees Fahrenheit, with small uncertainty. That is close to a bare rock regime without effective heat transport. Heat from day to night appears weak, or nearly absent. The direct implication follows. A thick atmosphere should move heat and cool the day. That picture is not observed. There is no evidence for a dense envelope. The quantitative frame is tight. Either the atmosphere is absent, or it is extremely thin, trace water vapor, and trace heavier molecules at parts per million levels. Tension with transit data emerges. Transmission through the stellar disk shows a persistent water vapor signature. But dayside thermal emission does not reveal a climate-scale gas effect. This is not an instrument mistake. The methods sense different layers. Transmission probes the rarefied limb at microbar pressures. Even a tenuous high-altitude haze can leave a spectral mark. A secondary eclipse measures the integrated heat of the entire dayside, meaning deeper layers, where a thin haze may be too weak to change the temperature balance in a measurable way. Two alternatives remain. First, an extremely thin, high-altitude water haze at the planet. It is visible in transmission yet dynamically weak, with little heat transport. This is better called a rare exosphere than a climate atmosphere. Second, the water signature originates on the star. Cool starspots on the red dwarf host stable molecular lines. Their contribution can mimic a water signature over a limited wavelength range when the planet occults regions with different temperatures and spectra, shaping a water-like transit curve without planetary gas. New brightness temperature estimates support exactly this fork. No thick envelope is required. The water signature in transmission remains. Choosing between thin haze and stellar spots requires wavelength, where the predictions diverge more strongly, plus a joint analysis of transmission and emission for the same system. Add monitoring across multiple stellar rotations to track spot modulation. Add short optical wavelengths, below 1 micrometer with time resolution across transit. Add phase curves and repeat eclipses to test energy transport and stability. Coordinated campaigns can cross-check reductions and isolate spot contamination. Bottom line at this stage is simple. The dayside of GJ486b behaves like heated rock with minimal heat transport. A thick atmosphere is not demanded by the data. The transit water signature is real, but its source remains open to interpretation. Starspots on red dwarfs are a cooler zone. Temperatures drop to around 4,000 degrees Fahrenheit and below. The surrounding photosphere sits near 6,000 degrees Fahrenheit. Under those conditions, molecules survive in spots, not outside them. Water, carbon monoxide, titanium oxide. Their lines stand out in the spectrum. As the planet crosses the star, it covers different regions. Sometimes a clean photosphere, sometimes a spot rich in molecules. Signals blend and can imitate a planetary atmosphere even when none exists. Separating stellar and planetary contributions requires added wavelength. The key is short wavelength, below 1 micrometer. That is where the models diverge most. Water vapor in a hot planetary limb gives one trend. Water vapor in cool starspots gives another. This difference is muted in the standard bandpass. NIRSpec operated from about 0.6 to 5.3 micrometers. That range is ideal for water vapor, near 1.4 and 2.7 micrometers, for carbon dioxide near 4.3 and methane near 2.3, but NIRSpec sensitivity falls toward 1 micrometer, exactly where the atmosphere versus spots curves separate. Hence the ambiguity of the transit water bump. A different setup closes the gap. NIRSpec targets the short wavelength down to roughly 0.6 micrometer. The method is single-object slitless spectroscopy, well suited to bright M-dwarfs. The full transit is time-resolved, so the signature's evolution is measurable. That enables direct tests of spot-linked variability. Diagnostic rules help. If the water signal strengthens toward shorter wavelength, a stellar origin is likelier. If it weakens or disappears, a planetary atmosphere is likelier. These tests need exactly the missing short wavelength coverage. Observations are approved, analysis is pending. Time variability adds another layer. Spots are uneven. The star rotates over weeks. The planet crosses changing zones. The signal may quiver in time. If the water comes from the star, amplitude and shape can drift. If the water sits at the planet, the curve should be steadier. 2 transits months apart showed the same result. The signature repeated, confirming a real water imprint. But ambiguity remained, either a thin, stable limb haze or a spot coverage, so high the planet keeps hitting molecular terrain. Without short wavelengths, a final verdict is not possible. This issue is acute for M-dwarfs. Spot coverage can reach 10 to 20% of the disk. Temperature contrast is large. Molecules in spots are robust. Every transit risks masking the planetary signal with a stellar one. The problem was predicted back in 2018 before the telescope launched. The physics differs across scenarios. A planetary limb is a rarefied, high-altitude layer. A light haze leaves a clear transmission imprint, yet barely affects day-night heat balance, hence a water transit with a bare dayside. The stellar mechanism is pure temperature contrast. A cooler spot with richer molecular lines. A cult part of it, and the system spectrum shifts. The transit curve acquires a water-like shape without planetary gas. Over a limited bandpass, the two are indistinguishable. Methodologically, 3 pillars matter: short wavelengths, timing, repeatability. Short wavelengths separate the spectral shapes of atmosphere and spots. Time resolution tests for within-transit variations over spotted regions. Repeatability confirms physics over noise and reduction choices. Add long baseline optical photometry to pin down rotational phase and spot filling factors. Eclipse mapping and phase curve snapshots to check day-night energy flow, and rigorous cross-calibration between NIRSpec and NIRS to stabilize modeling of limb darkening and spot contrast. Together, these controls raise the odds that the water we identify is truly planetary. If GJ486b has even a thin atmosphere, that's a precedent. We are talking about a rocky planet around a red dwarf. Orbit, about 36 hours. Dayside, around 865 degrees Fahrenheit. That temperature comes from secondary eclipses reported in August 2024. It sits close to a bare rock limit with no efficient heat transport. The estimate is roughly 97% of the theoretical maximum. That implies weak or near zero day-night heat redistribution. A dense envelope is not required by these data. The published conclusion is firm. No evidence for a thick atmosphere. Only an extremely tenuous layer is allowed. Less than 1% water vapor or carbon dioxide at parts per million levels. Yet transits consistently show a water vapor signature. Transmission probes the highest, thinnest layers. A high-altitude haze can produce the signature while staying dynamically weak. It barely affects heat flow, but still leaves molecular lines. If this configuration is confirmed, target selection shifts. Even rocky planets around active M-dwarfs can retain gas at the summits. Cooler worlds around the same stars become more promising. Lower irradiation, slower molecular destruction, higher odds of long-term stability. In that model, a steady source is required. Degassing or volcanic vapor from the interior is plausible. Geology must run for billions of years, feasible for a massive super-Earth. Actual geologic activity on GJ486b remains unproven. Even with a thin haze, this is not climate in the terrestrial sense. Pressures sit near exosphere levels, too little for strong heat transport, too little for surface shielding or weather. Still, the mere retention of molecules in an extreme setting is a survival signal. It widens the map of where to look for air around M-dwarfs. If there is no air at all, the picture flips. Red dwarfs produce flares, ultraviolet and X-rays. Such radiation accelerates escape of light gases and breaks molecules apart. Close-in rocky worlds lose atmospheres early in their evolution. A graveyard of atmospheres becomes a working hypothesis for M-dwarfs. Biosignature strategy shifts towards sun-like stars, rarer, harder to observe, which pushes timelines and demands stricter vetting. There is also a mass threshold. GJ486b is about 3 Earth masses, the upper super-Earth range. Stronger gravity should help retain gas. If even this world is bare, smaller rocky planets fare worse. If it is not bare, the stability threshold may lie lower. In both outcomes, habitable zone must be reinterpreted. Orbital temperature alone is insufficient. For M-dwarfs, the inner edge is set by atmospheric survival, not just liquid water equilibrium. A zone with a good temperature can be physically airless. One more fork sets priorities. If a thin haze is real, continue transmission spectra and expand wavelength coverage. If no haze exists, emphasize thermal maps and strict heat transport limits. A third path involves the star itself. Water-like signatures can arise from red dwarf starspots and mimic a planetary atmosphere in transmission. The bottom line carries high stakes. Thin haze exists. Hope for cooler M-dwarf systems. No air, evidence for an atmospheric graveyard. Stellar origin, a reset of methods and target criteria. Distinguishing among them requires additional wavelength bands and different instruments, and the next step is to specify which observations can separate these branches. New observations rest on 2 principles. First, a different window in wavelength. Second, a different signal geometry. Both are required because 2 honest methods deliver different inferences. Transmission during transit shows a water vapor signature. Secondary eclipses in August 2024 yield a dayside brightness temperature near the bare rock maximum and do not require heat transport by a dense atmosphere. To reconcile these, observations must cover shorter wavelength where the atmosphere and star spot models diverge. The region below 1 micrometer is critical. There, theoretical curves for water vapor in a rarefied planetary limb and water vapor in cool star spots separate most strongly. The setup that produced the initial water bump operates in the near-infrared out to a little over 5 micrometers and only grazes the 1 micrometer edge with declining sensitivity, hence the ambiguity. An almost flat spectrum with a rise at the short end. 3 independent reductions converge on water vapor as the likely cause, yet all acknowledge that stellar spots explain the data almost as well within that bandpass. This is precisely the gap a different instrument must close. In the reference it is labeled NIRSpec. Its job is to secure coverage from roughly 0.6 micrometer up to just below 1 micrometer with high sensitivity and time resolution across the entire transit. Time resolution matters. If the water signature originates on the star, amplitude and shape can drift as different spots are crossed. If the gas is planetary, the curve should be steadier. The diagnostic is simple in principle and demanding in practice. If the water imprint strengthens toward shorter wavelengths, a stellar origin is likelier. If it weakens or vanishes, a planetary origin is likelier. That is the requested test. NIRS observations are approved but not yet completed. Instrument time is scarce, and until publication the question remains open. In parallel, repeat transit statistics are building. 2 epochs, months apart, show the same short-end rise. That boosts confidence in the signal itself, but does not resolve the ambiguity. Either a thin, stable, high-altitude haze is real, or spot coverage is high enough that the planet routinely crosses molecule-rich regions. A second axis of new data is independent geometry. Secondary eclipses measure the integrated thermal emission of the dayside, and therefore test day-night heat redistribution. The August result, around 865 degrees Fahrenheit, roughly 97% of the computed bare rock maximum, does not require a dense envelope and thus does not confirm atmospheric heat transport. That, indirectly, strengthens the star spot hypothesis for the transmission-side water signal. Reliability also grows with processing discipline. Raw frames run through calibration pipelines. Teams push spectra through retrievals, Bayesian model comparison, and cross-correlation. For GJ486b, spot models and uncertainty budgets had to be upgraded. Separating planet from star at the few hundredths of a percent level is a new bar for rocky worlds. Cross-instrument calibration between the near-infrared spectrograph and NIRS, plus long baseline optical monitoring to track rotational spot modulation, further stabilizes the inference. On the horizon, added capabilities. The Nancy Grace Roman Space Telescope is expected to complement transit spectra with high-contrast imaging for the nearest systems. Extremely large ground telescopes with adaptive optics will add the photon flux and cadence needed to characterize nearby rocky planets. The outcome on GJ486b becomes a proving ground before the larger push toward cooler analogs. The new data plan reduces to clear steps. Secure short-wavelength coverage with time resolution. Unify transmission and emission for the same system. Replicate on several comparable M-dwarf planets and compare across epochs. Without short-wavelength coverage and NIRS, a final verdict isn't possible, and these same methods will carry forward to more promising targets. If the water signature is planetary, the search baseline changes. A rocky world around a red dwarf retains molecules under extreme heat. Cooler analogs become more promising. Irradiation is lower. Molecular destruction is weaker. The odds of a long-lived envelope rise. First rocky with air is not habitability. It is a survival threshold for gas in a harsh environment. A proof of principle, atmospheres around M-dwarfs are possible. Programs then shift to cooler orbits around the same stars. Targets with lower flux and softer radiation. Methodology shifts as well. Transmission must be paired with thermal emission. Short wavelength are mandatory to separate signals. Brightness temperature is mandatory to judge heat transport. Target selection standards tighten. Spectrum plus energy balance. If the water signature is stellar, the stakes flip. Cool star spots on an M-dwarf can imitate an atmosphere. Without short wavelength, background looks like air. Then, water claims on rocky worlds go under review. Tests for spot coverage and temporal stability become required. If there is no atmosphere at all, a graveyard of atmospheres emerges. Close-in rocky planets around M-dwarfs lose gas early. Flares, ultraviolet, energetic particles, everything works against envelopes. Priority shifts towards sun-like stars. Harder to observe, easier to interpret. Longer timelines. There is a mass threshold. GJ486b is roughly 3 Earth masses. Stronger gravity should help retention. If even this world is bare, smaller rocks fare worse. If it is not bare, the stability threshold lies lower. Institutional stakes are high. A planetary signal drives instruments tuned to rarefied limbs. Focus shifts to spectral stability and short wavelength. A stellar signal drives strict checklists for stellar activity. Focus shifts to joint planet plus star analysis as one coupled system. Both paths reward verification discipline. 2 independent methods, minimum. Repeatability over time required. Multi-system validation, goal for the next few years. That is how the verdict will land on GJ486b and on nearby analogues. The final wager is simple. Confirm an atmosphere, expand the map of where to look for air. Confirm starspots, strengthen filters against false positives. Confirm a bare rock, refine the inner edge of habitable zones. Logical next step, assemble what is established and what remains disputed with explicit criteria for future observations and time allocation decisions. The signal is real. Transit transmission shows a water vapor signature. 2 independent visits reproduce the same short-end rise. Instrument, the James Webb near-infrared spectrograph. Bandpass, roughly 0.6 to a little over 5 micrometers. Interpretation is contested. 2 physical models explain the same feature. 1, a thin water vapor haze at the planet's limb. The other, water vapor in cool star spots on the red dwarf. Within the used bandpass, both fit transmission nearly equally well. The ambiguity comes from the bandpass itself. Key differences appear at wavelengths shorter than 1 micrometer. Sensitivity there is limited, so separation is difficult. Additional observations are required with an instrument optimized for short wavelength. That request is filed under the name NIRSpec. A second window has opened. August 2024 delivered secondary eclipse results. This method measures dayside thermal emission when the planet slips behind the star. Brightness temperature, around 865 degrees Fahrenheit with small uncertainty. Roughly 97% of a bare rock maximum, implying weak day-night redistribution. A thick atmosphere is not required. Only a very thin layer remains allowed. So the picture unites facts that pull apart. Transmission says there is a water signature. Emission says there is little to no heat transport. 2 consistent frames resolve the tension. Either a high-altitude, dynamically weak water haze exists at the planet, or the water signature originates on the star, from spots on the M-dwarf. What supports the stellar reading? M-dwarf spots are cooler than the photosphere by thousands of degrees Fahrenheit. Under those conditions, water lines survive and contribute to the spectrum. When the planet occults a spot, the combined spectrum can mimic atmospheric absorption. Spot-filling factors can reach 10 to 20%. Stellar rotation moves spots across the disk on weak scales. Why the planetary reading remains viable. 2 transits, months apart, agree in shape. Independent pipelines converge on water vapor as the preferred molecule. Cross-correlation, Bayesian model comparison, and retrieval frameworks point to water vapor. Limitation noted. These tools prove water exists somewhere in the system, but without short wavelength, they cannot prove exactly where. Why separating star and planet matters. This is about inference quality at the sensitivity limit. Without clean separation, surveys will accumulate atmospheres that do not exist. M-dwarfs are active and spotted. Contamination is the rule, not the exception. Only a combined logic transmission plus emission plus short wavelengths is robust. The outer stakes clarify the context. If a planetary haze is confirmed, that would be the first confirmed gas on a rocky exoplanet. Method barriers would be considered crossed. Priority shifts to cooler M-dwarf analogs. If the signature is stellar, standards harden, short wavelength, and heat maps become mandatory gates. Either way, verification discipline strengthens, and the clean cases get cleaner. Why repeat observations? Repeatability averages down noise and catches spot variability. If the source is a specific stellar region, rotation should modulate amplitude and shape. If the source is the planetary limb, the curve should be steadier. Two visits match in form, but the models cannot be split without short wavelengths, where the models diverge. Below 1 micrometer, hot limb water vapor and cool spot water vapor predict different trends. One strengthens toward the blue, the other fades. A decisive test needs high sensitivity in the short band and time resolution through the full transit. That is exactly what NIRS is designed to deliver. Why secondary eclipses must not be ignored. They constrain energy balance rather than chemistry alone. The dayside of GJ486b behaves like heated rock. That regime does not require a dense envelope and shows no heat transport. What remains is either a rare, high-altitude water vapor exosphere or a stellar contribution to the water signature. The honest status today is straightforward. The water signal is stable and reproducible. Its origin is open to interpretation. Short wavelength coverage and a joint transmission-emission analysis can separate star from planet. Until those data arrive, keeping both versions in play is the correct scientific posture. We've reached a boundary where the facts hold a pause. Water is visible. The heat is quiet. Two explanations face each other: a thin haze at the limb or cool star spots on the dwarf. One word, atmosphere, redraws the search map. Another, mirage, rewrites the method. Between them lie short wavelengths and a single hard test. Choose accuracy over speed. Mistakes are costly. We'll wait for the spectrum to decide and only then say discovery. Whose water vapor signature are we seeing? The planets or the stars?